CH3 by the number 2. Then we end up with carbon 2, hydrogen 6. So this is how we determine the empirical formula and the molecular formula, one step at a time. Okay, so calculation involved in here isn't really, now all you need to do is to be able to punch in the number in the calculator. And the thing here is that you just need to know, how do we set up the equation? That's always going to be the challenge in this course here. And every time we introduce a new calculation, the key here is that you need to be able to identify the conversion factor. You need to be able to set up the equation properly. The calculation part isn't really that complicated, and it's not. It doesn't. The basic algebra and arithmetic sometimes. However, you need to know how we define certain things so that you know how to set up the equation. And once you know how to set up the equation, the rest of it becomes easy. Okay. So some examples about the percent composition, and here's a something that we can work together in class. We ask you to find the empirical formula of a compound from this particular data. So a compound has the following composition. Oops, gave you the answer already. Okay, and say percent composition by mass. We have 38.7% carbon, 9.70% of hydrogen, 51.6% of oxygen. Okay. Now remember the first step. We can assume we have 100 grams of this compound. So we ask you to determine the empirical formula. Okay. So if you assume 100 grams of sample, then we would have 38.7 grams of carbon and 9.70 grams of hydrogen, and then 51.6 grams of oxygen. Okay. So that's what that percentage composition means. And if you assume you have 100 grams sample, you can convert the percentage number back into grams there. What we need to do here is that we need to know how many moles. We're trying to determine the simplest whole number ratio. So 38.7 grams of carbon, each mole of carbon, 12.011 grams. So this will give you the mole of carbon. Each mole of hydrogen, 1.0079 grams. This will give you the mole of hydrogen. And each mole of oxygen, 15.9994 grams. This will give you a mole of oxygen. Okay. Once you get the number of moles here, if you want to punch in the number in the calculator, you can definitely do that. And once you come up with all the number of moles for these three elements there, you find the smallest number, okay, whichever is the smallest among these three. And then you divide every single number by the smallest number. The smallest number divided by itself equals to 1. Okay? And then the other number is bigger than the smallest number. When you divide those larger numbers by the smallest number, you come up with different numbers. So all we need to do is to come up with the whole number ratio. Okay? And in this case, happens to be carbon 1, hydrogen 3, oxygen 1. Okay? And the smallest whole number there. So 38 divided by 12, that's roughly about 3. 9 divided by 1, that's about 9. Okay? 51 divided by 16, that's roughly about 3. So it's a 3, 9, 3. The ratio would be 1, 3, and 1. Okay? So that's how we determine the empirical formula. And if you have questions about how to do this calculation, there, punch number in the calculator and make sure you get this formula. Okay? And another continuation, one more step here is that if we know the empirical formula in this case, carbon 1, hydrogen 3, oxygen 1. Okay. Now if we determine the molar mass of this compound to be 62 grams per mole, you can use mass spectrometer, you can use other methods there. Okay. We ask you to determine the molecular formula of this compound. Now CH3O, this is the empirical formula. Molar mass is 62 grams. There is a relationship between the empirical formula and molecular formula. All we need to do is to calculate the molar mass from the empirical formula. CH3O, carbon is 12, hydrogen is 1, 1 times 3, so that's 15. 15 plus oxygen, oxygen 16, you get 31. Okay, so in this case, and then we can determine the empirical formula multiply empirical formula, the molar mass divided by empirical formula will give you this whole number. Once you have this whole number, you can come up with the molecular formula. Okay, so and again, 62 gram is the molar mass of the compound. The molar mass, the formula mass for this equals to 31 gram per mole. Okay, so 62 divided by 31, that's 2. 2 times everything here, carbon 2, hydrogen 6, oxygen 2. That would be the molecular formula for this particular compound. Okay, so this is how chemists actually determine the actual structure of different types of compounds there. We need to know how much of each element is involved in there in terms of the percentage or in terms of actual grams there. Using the periodic table, we can convert everything back into moles. We can determine the molar ratio. Using mass spectrometer, we can determine molar mass. And from there, we can determine the molecular formula if we know the empirical formula and know the molar mass. Okay, so this is something that we have quite a bit of, quite a few questions in the homework assignment in chapter 3, asking you to do these kind of calculations there. Okay, so we run some of the examples in class there. And then another example there, find the molecular formula. If the empirical formula is carbon 5, hydrogen 8, molar mass determined from another method, say mass spectrometer, molar mass of a compound is 136 gram per mole. What is the molecular formula? Well, carbon 5, hydrogen 8. Carbon is 12. 12 times 5, that's 60. Hydrogen is 1. 1 times 8 is 8. So the formula weight, or empirical formula mass, for carbon 5, hydrogen 8, that's 68. Okay. 136 divided by 68 will give you 2. So the empirical formula is carbon 5, hydrogen 8. The molecular formula will be C5H8 times 2. That will be C10H16. That's how we come up with the formula. Okay, so that's the calculation. Now again, the calculation part itself is easy, basic arithmetic there. And however, you just need to know how we define empirical formula, how we define molecular formula. And once we know the molar mass, once we know the empirical formula, what's the relationship between those two different types of formulas there? One of the things that you will be doing in the lab today, you are going to be heating up an ionic compound, a hydrated ionic compound. So we talked about the formula of the nomenclature yesterday when we're doing the in the first order objective there. Now this red dot represents the chemical bond between water molecule and the ionic compound copper sulfate. Okay, so this particular dot, this is chemistry class there, not math class there. So if we ask you to find the molar mass of this hydrated compound, copper sulfate hydrate, you add copper, sulfur, 4 oxygen, and hydrogen, 5 oxygen together. You don't multiply that. Okay, this dot represents a chemical bond. Now you can determine how much water is present in hydrated compound experimentally. And this is what we will be doing today in the lab. We are going to ask you to use a little ceramic container, we call it crucible. Okay, you measure the mass of the crucible, and you record it. Okay, and the lab manual may ask you to clean up the crucible a little bit and wash it. And your instructor, when you go to the lab, there will say, don't wash the crucible, because every time you wash the crucible, the ceramic will actually absorb some water